So first we have our solid, like an ice cube. And in a solid, the molecules are packed tightly together, and which means they have a definite volume and a definite shape. Then you have your liquids. In a liquid, the molecules are packed moderately tightly together. So they're kind of actually moving as they're actually moving in a solid as well, but kind of shaking in a solid, and here they're kind of rolling, and they have a definite volume but an indefinite shape. A liquid is going to take the shape of its container. A gas, your molecules are moving even more randomly. They're far apart, and there's an indefinite volume and an indefinite shape. So why do we have the different phases of matter? Basically, you have your intermolecular forces, which are between molecules. And so you can see the intermolecular force here, which is between this molecule. You have your hydrochloric acid molecules, and here is your intermolecular attraction. All right. So a solid has the strongest intermolecular force, and gases have the weakest intermolecular forces. So intermolecular forces are between the different molecules. So if you have a water molecule here, you have the hydrogen bond, where the negative and the positive parts of your molecule are attracted. And you have different levels of intermolecular forces. So if you have a solid, it's low energy with a strong intermolecular force, and your molecules are moving, but they're just kind of shaking in place. A liquid has medium energy, a little bit more energy, and medium intermolecular forces, and the molecules are moving around a little bit more, kind of rolling around. And then in a gas, you have high energy with low intermolecular forces. So you have those elastic collisions. The molecules are very far apart compared to the size of them. And so they have very low intermolecular forces. So in our phase diagram, basically it's a graph where you can see all the three phases of a substance with two axes, which are temperature versus pressure. All right, so you can see the horizontal axis is temperature, and the vertical axis, like the Y, is pressure. And then you have, so this is a phase diagram for carbon dioxide. And so what you've got is at these temperature, any point right here would be a gas. At this temperature and this pressure, you have your carbon dioxide would be a gas. So if you're right here on the line, that's like where you're making a phase change from a solid to a gas, which would be sublimation, or from a gas to a solid, deposition. All right. And here you have temperature, a phase diagram for water. All right, so it's a phase diagram. You can see the solid right here, the liquid phase, and vapor is another word for gas. All right. I think we're going to talk more. So the important points here, one would be the triple point, which is right here. Okay, it makes sense because there's 1, 2, 3, lines coming out from it. So that's a triple point. All right. And that is where on the phase diagram where solids, liquids, and gases are all existing. Okay. It's going from a solid to a gas, gas to solid, solid to liquid, liquid to gas. All right. All these phases are happening at the same time. They all exist. And that is the triple point. Your critical point is the point where the solid, liquid, and gaseous phase can no longer be distinguished. All right, over here. It occurs at extremely high temperature and pressure. All right, so you cannot tell if you're a solid, liquid, or a gas. All right, and this is a review of the phase changes. So you have solid, liquid, gas. As we go from solid to liquid, that is melting. Liquid to solid is freezing. Okay, so those go back and forth. Liquid to gas would be evaporation, and gas to liquid would be condensation. All right, like when the water forms on the outside of your glass because the water vapor in the air is cooling down, so it goes to a liquid. Then you also can go straight from a gas to a solid. That is deposition. That's like the dew or frost on your car when the water vapor comes into, excuse me, that's like the frost because your water vapor is turning into a solid ice on your car. And then sublimation is going from solid straight to a gas, like dry ice. So what energy is involved with the phase changes? All right. So, and that is the key word there, is that when you're talking about phase change, you're talking about energy. So we got to think about what temperature is. Temperature is a measure of the average kinetic energy of the particles in a sample of water. And what is kinetic energy? That is moving energy. All right. And how that relates to phases is solids have the lowest amount of kinetic energy. The molecules are just kind of vibrating. Liquids have a little bit more energy. They're kind of rolling around. And then the gases have the most energy. All right, they have those elastic collisions bouncing off the walls, bouncing off each other, very spread apart. And here's a kind of a visual of that. Solid, liquid, and gas. Okay, and so the energy of a solid is less than a liquid, and the energy of a liquid is less than a gas. Okay, so solid, liquid, gas is going from least amount of energy to the greatest amount of energy. All right, so what is heat? Heat is the measure of the flow of energy from an object of high temperature to an object of low temperature. All right, everything goes from high to low, just naturally. So if you have, so heat is just energy moving from high temperatures to low temperatures. Heating and cooling curves are graphs of temperature, where you're looking at temperature versus heat. And what they show is the phase changes of a substance. So here's an example of a heating curve. Notice we have down here, your horizontal axis is you talk about how much heat you have. And here we're talking about temperature. Notice we're thinking of heat and temperature as different things. Temperature is the average kinetic energy. So, and then heat is that transfer of energy. So notice right here, all right, you have a solid state, all right? And that is as you're adding more heat, the temperature goes up. Okay, so you have a solid and it's getting warmer and warmer and warmer, right? And it gets to this point here, and it starts to, at this temperature here, it starts to go to the liquid state. Okay, so you're adding heat, but now it is melting. All right, I'm going from a solid to liquid. All right, so here is where I'm melting. I'm adding heat and I'm changing to a different phase. Now I'm in the liquid phase and I'm adding heat, but the temperature is going up. It's still a liquid. My liquid is just getting hotter and hotter and hotter. But at this point now, it's not getting hotter, all right? It's at this temperature over here. And it's not getting hotter, but I'm adding heat, and what's happening is it is vaporizing, or evaporating. Evaporation, vaporization, same thing. It's changing states. It's going from a liquid to a gas. I'm getting more and more energy, all right? But my temperature is staying the same. And then now here it's a gas. It changes to a gas. There's no more liquid. It's all gas, and the temperature is getting higher and higher and higher. All right? Let's see if I can go back. Remember, this temperature here is 0 degrees Celsius, where I'm melting and freezing, and where I am evaporating and condensing, that is 100 degrees Celsius. Okay, this is my boiling point, and this is my melting point. So how hot is hot? So we're going to think of heat as that energy transfer, all right? So you've got a new substance, you want to cook it up. So the question is, how much heat do you need to add, all right, in order to cook this substance? All right, well, how much heat is going to depend on how much you have, all right? If you're, if it's a hamburger, if you have a small burger versus a large burger, you're going to need less heat. Change in temperature. How hot do you want it to be? The hotter you want it to be, you're going to have more, you're going to have to add more heat. What substance is it? Each substance, if it's a metal, a non-metal, it's going to take a different amount of heat to change it. So we're going to put this together into a formula. We love formulas, and you guys are getting so good at doing formulas and using formulas. So we just need to know what each variable is. So Q is the heat that is absorbed, but it could also be released. And the unit is a new unit called a joule. And there's an Edpuzzle that will tell you about a joule. M is the mass of the sample, and that unit would be grams. C is the specific heat capacity. So that is how much heat it takes to change the temperature 1 degree Celsius. Okay, so that depends on the substance that it is. All right, and so that would be a table that you would look on to see that the specific heat capacity of your substance. Delta means the change, and then T is for temperature. All right, so this delta T would be the change in temperature. So there's my delta T. That's the change in the temperature. Okay, so you have this equation. You know what you do with an equation. You just substitute in what you're given, and then you solve for your unknown. So specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So let's try some problems. We've got, well, let's read it carefully, see what we're given. We've got the temperature is, we know the temperature is going to increase, all right? So that's my change, right? Increase means change. So I've got a change, and I'm going from 25 degrees to 78.8. So to get my, to get my change in temperature, I'm going to take my ending temperature, which was 78.8, and I'm going to subtract my starting temperature. All right, so go ahead and do that on your calculator. So you get 56.8. All right, no, 53. Right, 8 minus 5 is 3. Okay, so 53.8, and then that would be degrees Celsius. That's my change in temperature. And then I've got my grams here, so that's going to be my mass is 34.4 grams. And the question is how much heat, that was Q, right? Q is the heat absorbed in this case, right? It says heat is going to be absorbed. And then so I need to know, this is the specific heat for ethanol, all right? So the specific heat for ethanol is 2.44 joules per gram per degree Celsius. All right, so this is the amount of energy, joules is energy, that it takes to change 1 gram of ethanol 1 degree Celsius. Okay, so I've got my givens. My unknown is the heat absorbed. So now I'm going to write down my equation, which was the heat absorbed equals mc delta T. It's kind of like MCAT. All right. Even though that's a delta, that's a D, but it looks like MCAT. So now I'm going to substitute what I've got. The mass was 34.4, and my specific heat was 2.44, and my change in temperature was 53.8. And that is, I'm not going to put in units because I'm just doing the math and I don't want it to be. Okay, and so I get that, oops, oh man. I think I'm out of space there. So I get that Q equals 4,515, and I'll just take that to the tenths place, so that'd be 0.5.